Welcome back. This is video lecture 18.3, and we're going to discuss the content of chapter 18, section 5, in which we introduce for the first time the famous first law of thermodynamics. Remember, we already had the zeroth law of thermodynamics, which was about thermal equilibrium. We're not really going to use it anymore. The first law of thermodynamics, however, is very fundamental, as I will explain as we proceed. Now, one of the picture type ways of understanding the first law of thermodynamics, or a tool for helping us to understand the first law, is what's called a PV diagram. Here's how it's written, PV diagram. That's how you say it, PV. P for pressure, V for volume. Okay? Diagram means graph. We're going to graph with pressure on one axis and volume on the other axis. And we know how important graphs are and how much information they contain. Okay? We're going to use PV diagrams to apply the first law of thermodynamics. We're also going to be cycling back multiple times to do thought experiments and apply the first law of thermodynamics with practice in thought experiments. Those are experiments that you play out in your head. And the thought experiments we're going to use depend upon a very simple but very ingenious experimental device. Okay? And so what we're going to do is, with this experimental device, we're going to study exchanges of energy through work and heat between a system and its surroundings. The system that we're going to study is going to be a gas. Okay? A gas of some kind. Maybe it's nitrogen gas, or oxygen gas, or helium gas, or carbon dioxide gas. Some gas. And we're going to store it in a thermally insulated container. Now, the picture here is a schematic representation of this simple yet ingenious little device. Now, it's showing you a vertical cross-sectional slice, but what you have for your container is just a cylinder with thermally insulating walls around the sides, and then fit snug in there is a circular or disc-shaped piston. Again, here you see it in cross-section, that can move up and down inside the cylinder with no friction. Okay? All right. We have what I call a locking pin. It's this thing right here. Oops, it went away on me. Right there. Let's not stay. Okay. That has one job only, to lock the piston in place so that it cannot move. What does that do for us in terms of using this device to study a gas? It fixes the volume of the gas. The gas, by the way, is right there. Okay? In between the piston and the base of the cylinder. It shows those little green dots there. Those are supposed to make you think of atoms or molecules. That's just artistic license. The point is, that's the system, the gas, that is snug in there between the piston and the base, with thermally insulating walls around the side. On top of the piston is just a little container in which we have poured some little tiny, small metal, don't have to be metal, but small beads or spheres. They call it lead shot. First of all, it doesn't have to be lead. It can be anything you want. But the point is that there's a lot of them and they're each small. And that we can add more if we want, or we can take some away. Why would we do such a weird thing like that? Here's why. One of the several reasons why this is a clever little device. If you remove that locking pin or locking wedge, remember I said it's removable. If you take it out, then I contend that we, as the experimenters, can control the pressure of the gas. How do we do it? We do it with that little container with the lead shot on top. That is to say that as long as that locking pin's out of the way, then here's what's happening on that piston. There's a downward force from the weight of all those little lead shot and the weight of the piston itself on the gas, the weight of the piston itself on the piston. And then there's an upward force from the pressure of the gas. Remember, pressure is force divided by area. So in fact, that piston will always, as long as the locking pin's out so that it can move freely, will always adjust its position so that the pressure on the top and the pressure on the bottom are equal. Now, we control the pressure on the top by how many little lead shot we put there. Because the total pressure on the top is the atmospheric pressure down from the air plus the total weight divided by the area to get a pressure. All right? And so we control the pressure of the gas by controlling the downward pressure from the shot. We want more pressure in the gas, put more lead shot on top, make the pressure on top higher. We want less pressure of the gas, take some of the lead shot away to make the pressure on top to make the pressure on the top less. And the point is that the piston will always adjust its position so that the pressures on the two sides balance. So the pressure of the gas will equal the pressure from the shot. So that's the clever way that we control the pressure of the gas. We do it indirectly by controlling the pressure on top. Okay? And we will make, by the way, any changes to the lead shot very slowly. And that's why we want them to be small. Because adding one or taking one away at a time, very little effect. Just a little tiny incremental change. We don't pour a bunch of lead shot in all at once or scoop a bunch of lead shot away at once. We put them in or take them out one at a time, slowly. And each one is very small. So each addition or removal of a lead shot makes only a tiny change in the pressure on the top. The piston can then have plenty of time to adjust so that the pressure on the bottom balances. See what I'm saying? So we can, in a slow, very controlled way, adjust and change the pressure of the gas with the lead shot. Let me emphasize, this whole business of using the lead shot to adjust the pressure of the gas only works when that locking pin is out, because the piston has to be able to adjust. Okay? All right. Then there's that at the base. There's what the author calls a thermal reservoir. You might call it a hot plate. Notice it's got a kind of a knob labeled capital T for temperature. What they're trying to make you think of is you can turn that knob slowly, very slowly. If you turn it to your right, clockwise, kind of trying to make you think about higher, then energy will be added as heat from that hot plate thermal reservoir. And so there will be a Q into the gas that way. Q would be positive in that case. If you turn the knob to your left or counterclockwise to make you think down, then there will be energy transferred as heat Q out of the gas and into the reservoir. So with that thermal reservoir, you can control Q. Energy going in as heat to the gas or energy going out. And of course, by letting the piston move, you have work, W, as we'll talk about, okay? All right, so that's our very clever little device. And when we show PV diagrams and talk about various things happening in experiments, we're always going to often going to cycle back to this little apparatus and say, okay, how would you actually do the experiment that's being described to you with this apparatus? You'll see what I mean as we progress. But there's more to say about understanding this apparatus and working our way towards the first law of thermodynamics. And now I want to talk about a general way to calculate the work done by this system. Remember work from last semester? Okay. Forces do work. So I'm going to start with that. But we're going to end up with a formula for the work done by the system. In this case, the system, remember, is the gas inside that cylinder. That's going to be in terms of things related to this apparatus. So let me start by writing a little bit over here to the side. Let me remind you about how we calculated the work done by a system in terms of ideas from last semester. The whole point about work in this apparatus is that that piston goes up or down. Let's imagine that the piston moves up a little bit, a little tiny bit upwards. I'll call it ds for a tiny displacement, under a force, an upward force from the gas. Then the work done is just the force times that displacement, F times ds. And if I have a series of little displacements, one after the other, the total work done is the integral. Remember, integral is just a fancy sum of the upward force exerted by the gas on the piston times the successive tiny displacements, one after the other, ds. Okay? That's really physics 110. So I want to emphasize how we're not really changing that. We can't come up with a new definition of work now in the middle of everything. All right, but now what we do is we say, well, when you work with a gas, it's really the concept of pressure that's more useful. And pressure is force divided by area. In this case, the pressure of the gas, the force from the gas on the piston. Rearrange that. The force from the gas is the pressure of the gas times the area. So that's the pressure of the gas times the area A of the piston. This area of its face times the displacement ds. Okay, now here comes the next little trick. Take the circular area of the face of the piston this way and multiply by ds, which is a little displacement up, and you get a little tiny volume change, which is in fact the amount of extra volume the gas now has because it moved the piston up. So now we're going to write it as pressure times a tiny change in volume, a tiny volume increment, dV. That's what that means, dV, a tiny volume change. So this is the way we're going to calculate the work done by a gaseous system, such as the gas in that cylindrical container. We're going to have to do the integral of the pressure with respect to volume, P dV integrated from the initial volume to the final volume to account for the volume change. That's the integral we now use to calculate work done by our gaseous system. And that's what I've written down over here. Okay? Now, this notation, I've written it that way just to emphasize that it's the pressure of the gas as a function of its volume. We have to know that. If we're going to do the integral, we have to know how the pressure of the gas depends upon the volume, because it's an integral with respect to volume. I'm going to show you a little example here in just a minute. But I want you to understand that that's our expression for calculating work pretty much for the next two chapters, or this chapter and the next one. We do the integral of the pressure of the gas with respect to volume, starting at the initial volume and ending at the final volume. And here's a very simple thing to remember, but very useful. The work done by the gas is greater than zero, positive, if the final volume is larger than the initial volume. If the gas expands. And the work done by the gas is a negative quantity if the final volume is less than the initial volume. The gas contracts. Okay? That's also very important. There's a sign convention with work done by. Positive, work done by the gas is positive if its volume gets bigger, and negative if its volume gets smaller. Now I do want to say one more word about doing that work integral, W by. Giving myself a little bit of room here to write. In order to calculate the work done by our gaseous system, we must integrate from the initial volume to the final volume the pressure expressed as a function of volume, dV. We have to know how P depends on V. There may be more than one way, okay, that we will know that. But here's one way we might know. We might just be told. What if we are just told, well, there's an experiment that's been done where the pressure is a linear function of the volume. It's just some constant C times V. Okay? Where C is a positive constant. I mean, it's quite possible you're just going to be told that. Somebody has done an experiment in which they controlled the pressure and the volume together such that they were linearly related. How would you calculate the work done by the gas in a situation like that? You would substitute this form right here for the pressure as a function of volume, okay, right in the integrand. And then you do the integral. So let's do that. So now we're integrating from V initial to V final, a constant C times the value of V times dV. V, the volume, is the variable of integration. Now we use rules of integration, just like the variables, instead of V's, you had X's. It's the same thinking. C is a multiplicative constant, so you can pull it out front of the integral. So I have C times the integral from V initial to V final of V dV. Now that's the same integral as the integral of x dx, x to the 1 power dx, from x initial to x final. And I think you know how to integrate x to the 1 power dx. It's x squared over 2. And then all you got to do is put in the limits, but now we write it with v. So that's c times v squared over 2, with the limits being v initial to v final. So we get the following symbolic expression for the work done by the gas in this particular experiment. I've got a c over 2 out front. Then I have v final squared minus v initial squared. And if I've given that constant c the value, and I know the final volume and the initial volume, I plug in the numbers, and that's how much work was done. It's that simple. If we are given, or can somehow deduce, how the pressure depends on volume. Okay? And then we do the integral. Another possibility is we might be given a plot of pressure versus volume. And then the integral of P dV, an integral is area under a curve. And if the plot is pressure this way and volume this way, then it's just the area under the curve. That's the integral, that's the work. And of course, the plot of pressure this way and volume this way is called a PV diagram. Okay? So with a PV diagram for a given experiment, using our apparatus that I showed you, we can figure out, in some cases, actually get actual numbers for the work done by the gas. So now let me start showing you some PV diagrams. Okay? And start practice at interpreting them. All right, here is the first example PV diagram. Notice pressure on the vertical axis, volume on the horizontal axis. What you have to do in a PV diagram is you have to have dots to represent your starting state, like right there, and another dot to represent the ending state. Where did you start and where did you end up? Okay? So we're going to first do an experiment in which the first process goes from point I to point A. And so we draw the PV diagram, and it's this horizontal line going right across. That's part of the PV diagram. And there's an arrow on that little segment I just drew. That's important, not because I'm talking about vectors here, but because you have to know which way the process proceeds in the diagram. It could go one way or the other. This arrow points to my right. So I know I'm going to now talk about the process that I'm going to denote IA. That means going from point I on the diagram to point A along that horizontal line to your right. How would you describe that experiment, that process IA? Here it is, based on that picture. The gas expands because the volume gets bigger, right? Going to the right, the volume's getting bigger, at constant pressure. How do I know that? because it's horizontal line, and the vertical axis is pressure. So process IA, right from that diagram, I can tell you, is when the gas expands at constant pressure. Now here's a question I want you to think about. How would you do that process IA as an experiment using the apparatus I just showed you? How would you make the experiment proceed so that you get a PV diagram that like process IA using our apparatus? I'd like you to sit and think about that for a minute. Pause the video and think. And when you think you've got an idea, come back and we'll talk about it. Okay, have you thought about how to do the experiment IA? Expansion of a gas at constant pressure. Okay? All right, let's think about it. Here, I'll talk this one through in some detail so you understand what I want you to think about. First, I want the gas to expand. I want the volume to get bigger. I want the volume to change. I have to remove that locking wedge to even allow the piston to move up or down. That's thing one. Remove the wedge. Then I want the volume to get bigger. So I want the piston to go up. But I don't want the pressure of the gas to change, right? How do I get that to happen with that apparatus? Right? First, once the locking wedge is removed, how do you control the pressure of the gas? By controlling the pressure on top of the piston with the lead shot. You want the pressure to go up, add lead shot one by one. You want the pressure to go down, take lead shot away one by one. You want the pressure to be constant. What do you do with the lead shot? Nothing. Do not touch them. Then the pressure on top is constant. And therefore the pressure on the other side will always be constant. Remember, the piston will automatically adjust to make the pressures on the two sides equal. So don't touch the shot. That way you've kept the pressure constant. But I also want the volume to get bigger. How am I going to get that to happen? What's the only other thing I have at my control in the apparatus? I've taken out the locking wedge. I cannot touch the lead shot. What's the only other thing at my command? That hot plate or thermal reservoir at the base. What's your intuition tell you which way you should turn the hot plate if you want the volume to go up? Turn it up, i.e. add energy as heat. Okay? All right, that's how you would do process IA with our apparatus. Anyways, there's the PV diagram. Just looking from I to A. What I've also done is I've shaded the area. Well, I cross-hatched it. Now I'm going to shade it. I'm going to shade the area under the diagram from point I to point A. It's that yellow area I just shaded. That shaded area is the work done by the system for process IA. It may be hard to read. I labeled that WIA. And because the final volume, which is right there, is greater than the initial volume, or the volume at point A, I should say, is greater than the volume at point I, it expanded, then I know the work done by the gas is a positive number, not a negative number. When the gas expands, the work done by the gas is positive. And we also talked our way through on physical grounds that there will have to be energy added as heat. Q for process IA will also be greater than 0. Okay, that's process IA. But there's another step to this experiment number 1. Then we proceed from point A on the diagram to point F. Straight down, right? Vertically down. That's this next line segment going straight down with an arrow pointing down. You have to draw the arrows on the curves in the PV diagram so that they show you which way the process goes. So now you go from point A vertically down to point F. There's point F right there. Okay? That's what I call process AF. How would you describe it in words? Reduce the pressure of the gas at constant volume. Yes, going straight down, vertically down, means the volume is constant. But make the pressure smaller, right? Because we go down. All right, how would you do that with our apparatus? Pause the video and think about it, and then come back when you're ready. Okay, how would you use our apparatus to decrease the pressure of the gas, but not have the volume change? Well, how do you fix the volume of the gas? You have to be able to do it reliably. You put that locking wedge in, right? The locking wedge fixes the volume. That's how you fix the volume. Put the locking wedge in. Now remember, once the locking wedge is in, the piston can't adjust anymore. The little lead shots on top do nothing for you. Yet I still want the pressure to go down. So don't take lead shot. Don't say take lead shot away. It doesn't do you any good when the locking wedge is in place. Yet I still want the pressure to go down. What's the only other thing at my control? The thermal reservoir at the bottom. What does your intuition tell you for how I should turn that to get the pressure of the gas to go down? Turn it down. Have energy go out of the gas as heat. So one thing we know for sure is that there will be energy transfer as heat, Q, for process AF, and we expect that to be a negative number. We're going to have to take energy out as heat to get the pressure to go down. Note, by the way, there is no work done in this process. WAF is 0. You have to have a volume change to have work done. Okay, so for the total together, from I to A to F, that's the whole experiment, we could be asked what the total work and the total heat transfer is. And assuming we had numbers, what we would do to get the total work in going from I to A to F is just take the work in going from I to A plus the work in going from A to F. That last term happens to be 0. And the total energy transfer as heat, QIAF, is the energy transfer as heat for IA plus the energy transfer as heat for AF. Okay, and we've done experiment number 1. Now I want to do another experiment, experiment 2. And in experiment 2, we're still going to start at the point labeled I on the PV diagram. Same I point as in the first picture. And we're going to end at the point labeled F on the PV diagram. Same F point as the top picture. But now we're going to take a different path between I and F. One that curves a little bit like this. And notice the arrow. That's our new process. We'll just call it process IF. How would you describe it in words? Decrease the pressure and increase the volume together. Both things happening together. The pressure is going down and the volume is going up. That's what the graph shows. How would you do that with the apparatus? Pause the video, think about it, come back when you're ready. Okay? Now, how in general would you get our apparatus to follow a curve something like we see here in experiment 2? The key thing is what I just said. Two things have to be happening together. The pressure goes down and the volume goes up. Okay, so first, volume's going to change. So don't let that can't have that locking wedge in place. Otherwise, the volume can't change at all. Take out that locking wedge. The minute you do that, remember, you control the pressure of the gas with how many lead shots you have on top. So during the experiment, if I want the pressure to go down, what do I do with the lead shot? Slowly and one by one, take some away. Okay, that will make the pressure go down. But how do I get the volume to go up? What else do I have at my control? Because I want to make sure that the piston moves up. I have that thermal reservoir at my control, right? What does your intuition tell you for what to do to that if, as you take away lead shot one by one, you want the piston to go up? Well, you certainly think you want to add some heat. Okay? So we take away shot and we slowly add heat. Okay? I have cross-hatched the area under the PV diagram here. I'll shade it in now in yellow. It's the area under that curve. All right? Now that's a pretty complicated shape, so just using geometry there to get the area isn't going to be very easy. But that is the area under that curve, and the area under that curve is the work done by the gas. Okay? All right, so there's some work, WIF, and it's that area I just shaded. Now here's a question. How does the work done by the gas in experiment 2 compare with the total work done by the gas in experiment 1? Note that in both experiments, the gas starts at the point labeled I and ends at the point labeled F. But it takes different paths to get from I to F, doesn't it? Okay, in which experiment does the gas do more work? You might be inclined to think it does the same amount of work because the volume changes the same in both cases, but that's not true. Remember, in a PV diagram, the area under the curve is equal to the work done by the gas. So look at the two graphs in 1 and 2. Which has a larger area under it? Graph 1, yes? You're just going to look at them and see. So the work done in experiment 1, that's WIAF, is larger than the work done right here, which is this area, which I'll just call the work WIF. Or to say it another way, WIF is less than WIAF, even though the initial and final points on the diagram are the same. That's very manifest from the two diagrams. What isn't immediately obvious, but I will tell you, is that the heat transfers for the two experiments, QIAF for the first experiment, and whatever the Q is to complete the second experiment, QIF, they're not equal either. So there's a very important upshot to this first studying of PV diagrams. Both heat, Q, and work, W, are what we call path-dependent quantities in a PV diagram. Meaning, for a particular experiment, denoted in a PV diagram by going from one point to another, the amount of heat transfer and the amount of work depend upon the actual path the experiment takes from the first point to the last point. They're called path-dependent quantities. Which means you got to know the details of the PV diagram for the experiment before you can start figuring out Q and W. But it turns out from experiments that there is an energy quantity that doesn't depend on the path you take between one point and another in a PV diagram. All it depends on what is the starting point and what is the ending point. And it doesn't care how you get from the starting point and the ending point. That would be a path-independent quantity in a PV diagram. Okay? So there is a path-independent quantity in a PV diagram. And it turns out what that is, I will just denote, notice the delta symbol. Delta means change. Change in total energy of system. Delta E. Change, 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 change. The change in the total energy of the system for a given experiment does not depend on what path you take in a PV diagram, just on where was the starting point and where was the ending point. That's an experimental fact. Okay, now we're ready to state the first law of thermodynamics. Also an experimentally tested theory, okay? Or law. Something we call a law in physics means that it was started out as from somebody as some kind of hypothesis, and has been tested and tested and tested so many times by so many experiments that it is a given to be correct. Okay? All right, the first law of thermodynamics. What does it turn out to be at the very heart of it? Guess what it is? It is a very general statement of conservation of energy. Well, no wonder we know that's going to be true, because that's been thoroughly tested. That's one of like a fundamental physics principle, conservation of energy. Okay? Energy can't just be created or disappear. That's what it is. That's what the first law of thermodynamics is. It's a statement of conservation of energy. So here we go. Let's talk about it. As far as we're concerned at this point, there are two ways to transfer energy between a system and its surroundings. By means of a force, that method is called work, first appeared in Physics 110, and by means of a temperature difference between the system and the surroundings, which we called heat. So energy transferred by a force, work. Energy transferred because of a temperature difference, heat. Those are the two basic ways that a system can exchange energy with its surroundings. And if energy overall can't disappear, then the first law of thermodynamics goes like this. Whatever energy was added or taken out as heat, Q, plus however much work was done on the system, W, will show up as a change in the total energy. If I add 2 joules of energy as heat, Q, and 3 joules of energy as work by doing it on the system, W, then I will discover 5 joules of increase in the total energy of the system, because I added 2 joules by one mechanism, heat, and 3 joules by the other mechanism, work, or vice versa. Okay? Now, it could go the other way. The Q or the W on could be a negative number. If I take out energy from a system by heat, say 2 joules, then the Q is negative 2 joules. But still do 3 joules of work on it, then the W on is 3 joules. 3 plus negative 2, I'll discover a delta E total of only plus 1. It's just a balance. It's kind of like accounting. Okay? And that's kind of the way we did conservation of energy last semester. But what will never happen is that if there's a Q of 2 joules and a W on of 3 joules, then you'll discover delta E total is 6 joules, or 4 joules, or anything other than 5 joules. Okay? That's all it's saying. Now, we can hone this down a little bit. Delta E total is the change in the total energy of the system. Purely because it's convenient, we divide that into 2 parts. The change in the mechanical energy of the system, plus the change in what's called the internal energy of the system. Now, the change in the mechanical energy, remember mechanical energy from last semester, kinetic plus potential? Change in the mechanical energy is due to what you might call the external motion of the entire system, and it will correspond to some delta K from the motion of the center of mass, plus delta U from the motion of the center of mass. Then the delta E internal will be the change in the internal energy of the system. That's what's happening inside, due to the random motion and the interaction of the atoms inside the system. It's purely convenient to break it up like that. But here's what we're going to assume in this chapter. The center of mass of this thing really isn't moving. It isn't moving. I mean, imagine that apparatus I showed you at the beginning. For the center of mass to be moving, I'd have to be picking it up and throwing it across the room or pushing it along a table. We're not going to do anything like that. We did that kind of stuff last semester. The apparatus is just going to sit there on the table. And the motion of its center of mass isn't going to change. So there is no delta E mechanical. And the delta E total is purely happening internally. So now our conservation of energy law looks like that. Q plus W on equals delta E internal. Energy transfer is heat, plus work done on the system will correspond to a change in the internal energy of the gas. Then there's just one more change. Kind of a change of perspective. Instead of talking about the work done on the system, we like to talk about the work done by the system. But the work done by the system is just the negative of the work done on the system. So all you do is go into this right here and you change plus W on to minus work done by. And you get the statement of the first law of thermodynamics as we're going to use it in this and the next chapter. Q minus W by equals delta E internal. And it's an energy balance, so we have to be very careful with the signs of all three quantities, Q, W by, and delta E internal. And there's a rule for each. Q is positive if the heat transfer direction is into the system. Q is negative if the transfer is out of the system. The work done by the system, gas, W by, positive if the gas expands, negative if the gas contracts. Delta E internal, well, it'll be positive if the final E internal is larger than the initial E internal, and negative if it's the other way around. So now I'm going to close the lecture, the video, with just a little bit of practice and then a engagement exercise for you. So here's our first practice with PV diagrams and the first law of thermodynamics. We have, well, you can see we've got a PV diagram, pressure versus volume. We've got a starting point labeled I and an ending point labeled F. And we're going to do three different experiments represented by three different PV diagrams. All right? There's the first one below. See, it dips down and then goes over. Notice the arrow. That's process 1. Process 2 goes in a straight line pretty much from I to F. Process 3 goes up a little bit and then down from I to F. And process 4 goes up quite a bit and then down. But they all start at the same I and end at the same F. 4 distinct experiments with 4 distinct PV diagrams. First question. Rank the 4 paths according to the work done by the gas, largest to smallest. I'd like you to think about that, pause the video, and then come back. Okay, did you say that the work done by the gas depends upon the area under the PV diagram? That's what you want to say. Area under PV diagram. Now I am going to add one more thing. Multiply that by a sign, i.e. a plus or minus 1. Plus 1 if V final is greater than V initial. It expanded, so W by is positive. Multiply by the area by minus 1 if V final is less than V initial. It contracted. Notice that in both cases here, V final is larger. In all the cases here, V final is larger than V initial. The gas expands, the W by is positive. You don't have to worry about any negatives. So all you got to do is rank the work done by the amount of area under the curves, right? Which curve has the biggest area under it? And then the next, and the next. 4, then 3, then 2, then 1, right? You can look right at them and see that. So the ranking here for the W bys is it's biggest for 4, next biggest for 3, next biggest for 2, and smallest for 1. And we've answered A. Now let's go to B. Rank the paths according to the internal energy change, delta E internal of the gas, largest to smallest. Okay, think about that for a minute, pause the video, and then come back. Okay, now, here's a subtle point about this question. Remember, energy change, in this case internal energy change, is path independent on a PV diagram. It only depends on the starting point and the ending point. But all 4 of these experiments have the same starting point And they have the same ending point, right? Do you see where this is headed? All the delta E internals are equal. They all four tie. It's very important that you see that. Internal energy change is path independent on a PV diagram. So all four of those experiments result in the same delta E internal. Then we're left with part C. Rank the four paths according to the energy transferred as heat, Q, largest to smallest, worrying about positives and negatives too. Pause the video, think about it, and then come back. All right, now, you quite likely did a more kind of intuitive approach, thinking, well, in path 4, I had to have the pressure go way up before it came down. That's probably going to require a lot of heat. You know, it's all basically on how much pressure goes up or so forth or down between I and F. So you probably rank them 4, 3, 2, and 1. And that is correct. But now let me show you a more formal way to make that argument. Use the first law of thermodynamics. It's a very powerful tool. The first law of thermodynamics says that the change in the internal energy for any process is the energy transferred as heat, Q, minus the energy transferred as work, W by. Let's rearrange that algebraically and solve for Q. Do the algebra correctly. Q equals delta E internal plus W by. That you have to show that step. Now, use your answers from A and B to help you finish up here. From A, we ranked the W's. 4, 3, 2, 1. From B, we noted that the delta E internals were all the same. So the Q ranking is determined entirely by the W by ranking, and they're the same. So Q, in order, is 4, 3, 2, 1. You need the most heat, and they're all positive, because the W by's are all positive in this case. So you need the most heat for experiment 4, Q. And then the next most for experiment 3, and then 2, and then 1. And that's a lot of stuff you're saying at a very fundamental basic level from a very abstract diagram. If you want, you can think about how you might do those experiments with the apparatus. Okay, here we close today with our class engagement exercise on Blackboard. More practice with PV diagrams and the first law of thermodynamics. This figure shows two what we call closed cycles on a PV diagram for a gas. What's a closed cycle? Well, it's a PV diagram that starts at some point. Let's say in both of these two pictures, the starting point, I'll put a red dot, is this lower left corner. Starts at some point and proceeds by a series of steps, okay, in this case 3, and gets back to the point it started from. That's the key thing. You start at a certain point in the PV diagram, you go through a series of steps, and you end up back where you started. The resulting PV diagram is closed in on itself, so it's called a closed cycle. The 3 parts of cycle 1 are the same length and shape as those in cycle 2. In other words, that curved part right there and that curved part right there are exactly the same. That horizontal part there and that horizontal part there, exactly the same. That vertical part and that vertical part, exactly the same in those 2 diagrams. Or cycle. Here's the first question. For each cycle, should we traverse the cycle clockwise or counterclockwise? If the net work, W by, done by the gas is to be positive. You see, with each experiment, you start down the lower left corner, you could go traverse the experiment counterclockwise. That means That would be the direction of each successive segment. Or you could traverse counterclockwise. You could go first that way, then that way, then that way, and end up back where you started. Clockwise or counterclockwise. You can do each one that way, starting in that lower left corner. So for each cycle, cycle 1 and cycle 2, which way should you traverse? Clockwise or counterclockwise if your goal is to have W by for the whole cycle to be positive. Question B, for each cycle, should the cycle be traversed clockwise or counterclockwise? If the net energy transferred by the gas as heat, Q, is to be positive. Those are the two questions. So you'll have an answer in part A, you'll have an answer for 1, cycle 1, and then cycle 2. And for part B, you'll have an answer for 1 and for 2. You do that on Blackboard. Okay? All right, we'll be talking about this also in class. And that's all for this video.